So a very warm welcome to the second day of the Fisher Conference, both to those in the room and those joining us online. Now, first contributor today is Qingyuan Zhao from the Statistical Laboratory here in Cambridge. So he's an assistant professor in the Stats Lab and also a fellow of the Alan Turing Institute and of Corpus Christi College. Qingyuan did his undergraduate work in the University of Science and Technology in China and his doctoral work at Stanford. And his research interests include causal inference, high-dimensional inference, and applications of statistics to various fields, including genetics, epidemiology, and social sciences. So in addition to working at these cutting edges of the subject, he also, well before this conference was really starting to be planned in detail, had made a number of interesting posts reflecting on the sort of historical development of statistical ideas, including contributions by Fisher. So it's a real pleasure to welcome him today. He's also joining us by Zoom, so we're especially grateful to him for soldiering on in these difficult circumstances. I think the worst of his COVID symptoms are now abating. But we're very grateful for you to speaking to us nevertheless. And the title is going to be Fisher, Statistics, and Randomization.
Thank you. Thank you very much for the introduction. Thank you to everyone who is involved in organizing this wonderful conference. I must first apologize that I'm not able to give this talk in person. I unfortunately caught the coronavirus last week, and I'm still experiencing lingering symptoms. I've been anticipating this conference for the last year, and it's a real shame that I can't be there with everyone in the auditorium. I want to thank the organizers for allowing me to speak virtually. So the title of my talk today is Fisher, Statistics, and Randomization. Yesterday, we heard Professor Reed and Professor Aston give us two really interesting talks about Fisher's immense influence on both theoretical statistics and applied statistics, or data science. Both of them did a great job bringing Fisher to the 21st century. My plan today instead is to mostly talk about some historical aspects in Fisher's work in statistics, especially his philosophical considerations in statistics and some of the controversies he was involved in. In doing so, I'm using one advantage that I have, that is I received almost all my education in the 21st century, so I don't need to try too hard to justify Fisher's relevance in this century. This doesn't mean that I don't know anyone who personally knew Fisher. So Fisher is really a historical figure to me. So the Fisher I will talk about today is inevitably constructed from my reading of Fisher's writing and the stories told by people who knew Fisher. And it's perhaps an incomplete image of Fisher. So every statistician has heard about Fisher's name countless times in their training. And in Professor Reed's and Professor Aston's talk yesterday, we learned how many ideas of Fisher are sort of lurking in the statistical literature without his name really being mentioned. But I think, to be honest, Fisher has been a mystery to me and perhaps most other statisticians. Especially I'm talking about this very productive time of his as a statistician between 1915 and 1935. So I was always wondering, how did he have so many great ideas in such a short span of time? So while preparing this for this talk, I've taken the opportunity to read some of Fisher's work. Okay, so there's several of Fisher's work that will be mentioned in this talk. There are two of his books, The Statistical Methods for Research Workers from 1925, and The Design of Experiments from 1935. So these are his two classic books in statistics. There are also a number of articles which are span across several fields. This 1915 article is the paper where he derived the students' T distribution rigorously. This 1922 paper, this is what Professor Reed mentioned many times yesterday, where he laid the foundation of theoretical statistics. This 1923 paper is the first place where the analysis of variance appeared. This 26 paper is where Fisher first elaborated on randomization, which is the focus of this talk. This 1947 paper, Fisher gave a review of his involvement in the development of experimental design. This 1952 paper is really an article, the text for his lecture, his Bateson lecture in a year earlier, given to geneticists, but it is a rare place where he linked his work in statistics and genetics. This 1955 paper, this is where he criticized the Neyman-Pearson theory and the Wald decision theory. And finally, this 1958 paper, he discussed cancer and smoking. So here's the outline for my talk. I'm first gonna talk about Fisher and his involvement in randomization. In doing so, I'll try to talk about his involvement in three kind of distinct roles that randomization plays in statistics. Then I'll talk about Fisher and design of experiments, how his work in genetics and statistics interplayed, Fisher and non-randomization studies, especially his criticism of the Doe and Hill study on smoking and lung cancer. If I have some time, I will try to go over very briefly his controversy with Neyman. It's not quite related to randomization, but I've thought maybe nobody else will mention this in this conference, so I might just use some time to say a few words about that. Then I'll conclude with some personal reflections. Okay, so first, Fisher and randomization. So randomization is Fisher's first principle of experimental design, and it has profoundly changed how modern science is being done. This is perhaps one of Fisher's most influential contributions to science. So randomization is first mentioned in his statistical methods for research workers in 1925, but he did not elaborate on that. A full extension of this idea is given in his 1926 paper, and finally he gave a very developed account of randomized experiment in his design of experiment book. Okay. So nowadays, we just take randomization for granted. When we talk about experiments, we directly link that with a randomized experiment most of the time in statistics. But this was not really the case even decades after Fisher's design of experiments. And one example I'm giving you here is in a letter that William Gossett, who is also known as the student who discovered the student's T distribution. He's a good friend of Fisher, and he repeatedly disagreed with this point that we should randomize our experiment. So this is a quote from Gossett's letter to Fisher after he proofread Fisher's statistical methods for research workers. So in opening that letter, he said, "I do not expect to convince you, but I do not agree with your controlled randomness. You would want a large lunatic asylum for the operators who are apt to make mistakes enough even at present." So Gossett is trying to use his humor to say that he doesn't agree with this point, that we should randomize our treatment assignment. So to discuss randomization, because it's such an interesting and broad idea, I thought I'm going to use this summary by David Cox that really breaks down the role of randomization into three. The first role of randomization is to avoid selection and other biases, and do so in a publicly convincing way. The second role of randomization, as Cox summarizes, to provide a unified approach to the analysis of many standard designs of experiments. And the third role is that randomization provides a basis for exact tests of significance and related interval estimates. So first role, avoid hidden bias. So this really goes back to some work that's before Fisher. So it turns out that before Fisher, randomized experiment had been used in psychological experiments. And this prehistory is really very well, nicely reviewed by this paper by Ian Hacking. So the first randomized experiment is believed to be this one by Peirce, Charles Sanders Peirce, is an American philosopher, and his student, so Jastrow. So in that experiment, Peirce and Jastrow were trying to test if there is a threshold in our sensation of pressure. So what they did in the experiment is they let the subjects first experience a weight of 1 kilogram, and then they either add a little bit of weight to that 1 kilogram or remove a little bit of weight from that 1 kilogram. And then they let the experimental subject to experience it again. And eventually the subject needs to decide which one is heavier and which one is not. So the key thing for today's talk is that this order, that whether the second weight is heavier or slightly lighter, was determined by a well-shuffled decks of cards. And Peirce and Jastrow thought that was important to eliminate personal biases. So Peirce used this experiment to sort of demonstrate the possibility of certain sort of telepathic phenomenon, that maybe it's possible that I can telepath my thoughts to someone else. And across the Atlantic Ocean in France, there also this physician, Richard, also tried a similar kind of experiment where he wants to answer the question about our ability to detect weak powers of telepathy. So he used a long sequence of trials in which an agent draws a playing card at random, and then the agent concentrated upon that card for a short time, after which a reagent guessed the suit of the card. And this is another instance of randomization being applied. And somehow in this very beginning of this kind of psychophysics research, randomization was really sort of useful to eliminate personal biases in considering these kind of phenomenon about telepathy. And Hacking's paper mentioned another series of work by Coover, who's an American psychologist based in Stanford, who started a series of experiments from 1912 that not only randomized the card, but also whether the trial would be regular or control, meaning whether the agent actually looked at the card at all. So Coover also randomized that aspect of the experiment. So before Fisher really sort of went to this field of experimentation, so there are these sort of work in psychophysics that sort of argued for the use of randomization. And indeed, after Fisher's work, Bradford Hill is also very well known for his forceful argument for randomization in the context of clinical trials. So that happened sometime, I think, around 1940s and 50s. The psychologists and Hill, however, they emphasized on how randomization eliminates personal idiosyncrasies and confounding bias. So they really were trying to use randomization as a device to eliminate those sources of bias. But the psychologists and Hill, they did not give a very mathematical account for why randomization could eliminate bias. So Fisher, of course, knew this point, and he clearly expressed this point in this sentence in the design of experiment. So he said, randomization properly carried out relieves the experiment from the experimenters, from the anxiety of considering and estimating the magnitude of the innumerable causes by which his data may be disturbed. And nowadays, this innumerable causes is commonly called unmeasured confounders, a terminology also, I think, due to Fisher. So Ian Hacken's conclusion when he reviewed this prehistory was that Fisher was well aware of the psychophysics research, but Fisherian randomization really involves a very different level of sophistication. And Fisher is sort of the first person that really gave a mathematical justification of randomization, and he sort of forcefully argued for randomization, and that really helped laying out the foundation of this idea in scientific research. So the second role of randomization is the mathematical justification that randomization brings for experimental inference. And this is where Fisher, I think, really forcefully argued. So this started when Fisher studied small sample statistics. So Fisher started to correspond with William Gossett, aka student, in 1912, and he worked on the statistics of small samples. So in his 1915 paper, he gave a mathematical proof of Gossett's result. So this is a quote from the first page of that paper, where he said, this result, meaning the result derived by Gossett, which was not really a rigorous proof, it was more like a conjecture. So Gossett computed the first 4 moments of the T distribution, but he did not prove this is the actual distribution. So the Fisher is saying this result, although arrived by empirical methods, was established almost beyond reasonable doubt. But the form establishes itself instantly when the distribution of sample is viewed geometrically. So what Fisher had in mind is this geometric argument that involves representing n observations as a point P in an n-dimensional space. So basically, this is his from his 1915 paper, where he is considering 3 data points, x1, x2, x3, and he's imagining this point x1, x3 is in this 3-dimensional space, and then he could capture the variation from P from the average M, which is this on this diagonal line that x1, x2, x3 are equal. So P is the distance between P and that line is sort of the variation of the data. And Fisher used this intuition to calculate the T distribution. Although this exact calculation is not as straightforward as Fisher described in this quote. And Fisher repeatedly used this intuition in the next decade. And it's believed that this is really related to his conception of randomization. So after being appointed as a statistician at the Rothamsted Experimental Station in 1919, Fisher started to connect the geometric idea with randomization. So in his 23 paper, where the analysis of variance was first introduced, Fisher said, if all the plots are undifferentiated, as if the numbers had been mixed up and written down in random order, the average value of each of the 2 parts of the sum of squares is proportional to the number of their degrees of freedom, respectively. In the 1926 paper, where Fisher extended this idea of randomization, he said one way of making sure that a valid estimate of error will be obtained is to arrange the plots deliberately at random, so that no distinction can creep in between pairs of plots treated alike and pairs treated differently. So as you can see here, Fisher is really mixing up these two ideas, that randomization eliminates bias and randomization eliminates or justifies the statistical analysis of uncertainty. So Fisher went on and said, in such a case, an estimate of error derived in the usual way from the variations of sets of plots treated alike may be applied to test the significance of the observed difference between the averages of plots treated differently. So you can see here that Fisher's justification of randomization clearly differs from those of the psychologists and of Bradford Hill. So he really emphasized on randomization's role in correctly quantifying variance or the statistical error. So Fisher's geometric intuition is nicely described by his daughter and biographer Jean Fischer-Box in this paper in 1980. So there, Box suggested that Fisher could have justified his statement that the sum of squares of those terms have the degrees of freedom respectively to each of the terms. So Fisher could have justified that statement by assuming normality and independence, but he did not choose to do that because he was convinced that those assumptions are not needed if one randomizes. So this is from this paper by Box. So she said, his confidence in the result, however, depended on the geometric representation that was by then second nature to him. He could picture the distribution of n results as a pattern in n-dimensional space, and he could see that randomization would produce a symmetry in that pattern rather like that produced by a kaleidoscope, and which approximated the required spherical symmetry available, in particular from standard normal theory assumptions. So Fisher's thinking was really motivated by this geometric consideration. However, when I read this and tried to read what Fisher wrote in his original articles, I still find it a bit of a mystery what Fisher precisely had in mind. So in a standard theory for analysis of variance, where we assume normality, a key result is that if you look at the norm squared of a projection, this projection P times this random variable y, which follows a normal distribution, then that sum of squares, that norm squared, would follow a chi-square distribution, with the degrees of freedom being the trace or equivalently the rank of that projection matrix. So Fisher must have seen that such a result is approximately true if this y does not follow a normal distribution but is in some sense randomized. But it seems that some conditions on randomization is necessary, and Fisher never really, as far as I know, sort of gave those conditions. So one example is that if you look at the expectation of the sum of squares, then that's this trace of P times the covariance matrix of Y. So Fisher said in his analysis of variance paper that this should be proportional to the degrees of freedom of P. But that's really only exactly true if the covariance Y is proportional to the identity matrix. So this would almost hold for the permutation distribution, but not quite precisely. So it's a bit of a mystery what Fisher precisely meant when he wrote down those statements. And I guess we've seen yesterday that this is not it's not specific to his work in statistics. That, for example, his fundamental theorem in the genetic theory that was also not described very precisely in a mathematical way. So I'd like to mention that there is actually a formal connection between the normal theory distribution and the randomization distribution, and that was established in the 1950s by Oscar Kempthorne, and that formal connection requires some additional assumption called additivity, meaning the treatment effect is homogeneous. I'm sorry, it's homogeneous across the experimental subjects. Okay, let me move to the third role of randomization. That is, you can use that to construct a randomization test. So this quote from Fisher, that basically from the design of experiment that basically established this idea. So there, Fisher was trying to defend his assumption of normality. So he said there has been a tendency for theoretical statisticians not closely in touch with the requirement of experimental data to stress the element of normality, as though it were a serious limitation to the test applied. In these discussions, it seems to have escaped recognition that the physical act of randomization affords the means of examining the wider hypothesis in which no normality of distribution is implied. And in his book, Fisher gave an example. So this is a pairwise randomized experiment where there are 15 pairs and you get 15 numbers which corresponds to the difference between cross and self-fertilized plants within the pair. So Fisher said there's the sum of these 15 numbers, taking account of the two negative signs which have actually occurred, is 314. And we may ask how many of the 2 to the 15 numbers, which may be formed by giving each component alternatively a positive and negative sign, exceeds this value. So he indeed did this computation in his book, and he listed the number of cases that these sum would exceed 314, and he found that the randomization p-value is roughly 0.05, which is quite close to the p-value of a t-test. And Fisher used this as empirical evidence to justify the use of t-test and analysis of variance in experimental inference. I want to stress 2 points. First, that this test based on randomization entirely rests on the physical act of randomization, and no modeling assumption is needed. And this is seen not as a very important point by Fisher, but it was valued a lot, especially by theoretical statisticians. And this is where sort of non-parametric statistics was kind of first derived from. And indeed, this idea has been repeatedly rediscovered and sort of reapplied to new contexts, even very recently. Okay, my second topic of the day is Fisher and design of experiments. So here I'm gonna quote from this article by Fisher that best describes how his view has shifted regarding the design of experiments. So Fisher was brought in the Rothamsted's experimental station as a data analyst, as we may call it today, or data scientist, to examine a great number of files of records. And that was also his expectation. So he said, at the time, nothing was further from my thoughts or from those of my contemporaries than that the art of experimental design would ever come to be, as it now surely is, an integral part of the subject. The horizon was indeed filled with problems of estimation. So this is also what Fisher initially looked at, and he developed the theory of the maximum likelihood estimator. So it was rigorously demonstrated that the amount of information extracted in the process of estimation could never exceed the quantity supplied by the data. So this, Fisher was referring to his foundational work regarding maximum likelihood estimator and information. But one philosophical consequence of this result to Fisher is that this really changed the role of the statistician. So in his words, he said, this finding shifted the moral balance. His business became much less like that of a conjurer who is expected to work wonders. And I think this is, in some sense, kind of like a modern day data scientist, where we were brought in to analyze some data and we try to come up with some really interesting conclusions. So Fisher said the role of statisticians become less like that and more like that of a chemist who undertakes to assay the proportion of gold in a sample. The weight of his responsibility was thrown back onto the process by which the data had come into existence. And by this, I think Fisher was referring to how the experiments are designed. So I'm going to talk about two designs that Fisher championed. The first is sort of randomized blocked design. So blocking is indeed one of Fisher's principles for experimental design. And the link between blocking to Fisher's analysis of agricultural experiments is quite clear. Because when you think about a field, then observations of the fertility of adjacent field, plots were known to be highly correlated, and we have rows of fields when we plant these when we grow the plants. So really, I think Fisher was sort of seeing that as a way, by sort of blocking the adjacent plots, as a way to control for unaccounted variation. So intuitively, you would like to use a more balanced design that assigns treatments equally often in each block. And Fisher rigorously showed that by adopting such a design, we could isolate and eliminate the variance due to block differences. And this greatly improves the efficiency of his analysis of variance. So here, Fisher really demonstrated that a better way to getting the data can reduce variability and improve the efficiency of the statistical analysis. The second design I'll talk about is the Latin squared design, which is very well known for, and probably why we're all here. And in his Latin squared design, this you can see a really close resemblance to agricultural experiment. So basically, here you have 5 rows and 5 columns. And then this design allows one to have one treatment, every kind of treatment in every row and every column. So this row is a permutation of A, B, C, D, E, and this column is a permutation of A, B, C, D, and E, and this row is also a permutation of A, B, C, and C, D, and E. So this design really allows us to block 2 factors, the rows and the columns, simultaneously. And I think it's really an extremely elegant design, even though it's not used as often as Fisher had hoped for, perhaps these days. I think this is really an elegant design that demonstrated Fisher's talent and contribution in combinatorics, geometry, and statistics. I think it's really a good embodiment of how great Fisher as a mathematician and a statistician was. Next, I want to talk a little bit about the interplay between Fisher's work in genetics and statistics. So they indeed interacted strongly, and the most notable examples are the use of variance, which was mentioned yesterday by several speakers, and the development of factorial experimental designs. So as mentioned yesterday, it's in Fisher's study of genetics that he first coined this term variance. So in doing in doing so, Fisher was really trying to dealing with a way to decompose the variability of the data, and he found that the square of the standard deviation is sort of a really nice measure of variability that allows him to decompose. I'm gonna skip this reading this quote, but I do want to read this quote from his 1952 article, which is basically the lecture, the Bateson lecture he gave 1 year earlier, where he described this other link between genetics and statistics. So Fisher said, and here I may mention a connection between our two subjects, which seems not to be altogether accidental, namely the factorial method of experimentation, now of lively concern so far afield as psychologists or the industrial chemists, derives its structure and its name from the simultaneous inheritance of Mendelian factors, or AKA genes. So really, when Fisher brought up these factorial designs to experimentation, the motivation came from Mendelian genetics. Another point I wanted to raise, and this is more like a speculation of Fisher's original idea about randomization. I mentioned earlier that it's perhaps rooted in his geometric intuition of the normal distribution and randomization. But it would be a reasonable speculation, I think, to say that it's perhaps also seated in his understanding of Mendelian genetics. Fisher never said this very explicitly, and perhaps I think it's perhaps so hidden in his subconsciousness that maybe he never mentioned it. But I have some evidence, and this is brought to me by Professor George Davis Smith at the University of Bristol. So one evidence is understanding of Mendel's theory in terms of frequentist probability. So in this paper by by Bernard, who reviewed Fisher's contribution, he mentioned Mendel's theory, and he said Mendel's theory was the first in natural science to express its experimental predictions in terms of exact frequency probabilities. For example, that the probability that a P from a certain type of cross will be round rather than wrinkled is 3/4, not approximately 3/4, but exactly 3/4. But the idea that nature itself could behave like a perfect gambling machine was revolutionary. So really, Bernard was trying to say that this Mendel's theory gives us a first instance of this kind of frequency probability that would occur in repeated experimentation. And Fisher, of course, knew this point by his heart. And Fisher, in the 1952 or 1951 Bateson lecture, also mentioned how important this randomization is to geneticists. So he said, genetics is indeed a peculiarly favored condition in that providence has shielded the geneticists from many of the difficulties of a reliably controlled comparison. The different genotypes possible from the same mating have been beautifully randomized by the meiotic process. A more perfect control of conditions is scarcely possible than that of different genotypes appearing in the same litter. So it appears that when studying genetics, Fisher was really well aware of this point, that a lot of his studies was shielded from these unmeasured confounders because of this Mendelian randomization that occur in inheritance. Okay, I probably only have time to go through the Fisher and non-randomization my studies, and I'll skip his controversy with Neyman. So I wanted to say a little bit about Fisher and lung cancer and observational studies. So I'm going to be very brief about this background because I think we'll hear more about this story later on today. So over 1950s, several studies revealed a large and robust association between smoking and lung cancer. This prompted this declaration in the British Medical Journal in 1957 that the most reasonable interpretation of this evidence is that the relation is one of direct cause and effect. So Fisher wrote several letters and articles to voice his objections to this conclusion. And his main concern was the following, and I'm using a quote from his 1958 letter to Nature. So he said, such results suggest an error has been made of an old kind in arguing from correlation to causation, and that the possibility should be explored that the different smoking classes have adopted their habits partly by reason of their personal temperaments and dispositions, and are not likely to be assumed to be equivalent in their genotypic composition. So basically, Fisher's concern was precisely on measure confounders, and he, of course, knew very well how randomization eliminates unmeasured confounders, and why causal conclusions can come from a randomized experiment. So he's basically trying to say that if the evidence entirely comes from some observational studies, some observed correlation, that does not immediately justify causation. And of course, Fisher objected to also the conclusion of these studies, and he tried to provide some data to back up his argument here. So being a geneticist, he, of course, tried to look at some genetic data, and he provided some data that showed monozygotic twins or identical twins are more likely than dizygotic twins or fraternal twins to have the same smoking habits. So this suggests that smoking is at least partly heritable. So there are indeed some genotypic explanations of smoking, and these observational studies of smoking and lung cancer did not take that into account. Now, Fisher was criticized on several fronts on his own criticism of the lung cancer studies. This occurred both at the time by many epidemiologists, but also later on. So this quote was from an article in 1991 titled "When Genius Errs, R.A. Fisher and the Lung Cancer Controversy." And there the author said Fisher's analysis was incomplete and used highly selected data, or no data but much speculation, with scant attempts to weigh the evidence or reveal the obvious deficiencies in his data. Fisher sounded like a man with an axe to grind. Fisher was unwilling to seriously examine the data and review all the evidence before him to try to reach a judicious conclusion. I think there are several things that I think we need to at least be aware of when we evaluate this controversy that is not always presented. First, Fisher never denied the possibility that smoking could cause lung cancer. He was mostly concerned with the logic behind this conclusion. He accepted the invitation of the Tobacco Manufacturers Standing Committee to be their scientific consultant in 1956, and this drew a lot of criticisms. But I think according to his daughter, John Fisher Box, Fisher believed receiving payments for doing so should not influence the nature of his advice. And this was perhaps in the time where the ethics of research and declaring conflict of interest was not so well established as today. And the third point is something I found when I really tried to look at the randomization trials of smoking, and I couldn't find many. And to my knowledge, even today, there is no direct, like, gold standard evidence that Fisher requested I'm only aware of 2 randomized clinical trials in the 1970s and 80s on smoking cessation, and none of these trials was large enough to provide a definitive conclusion on the benefit of quitting smoking. So in some sense, we have to entirely rely on observational evidence when thinking about the causal effect of smoking. And I think Fisher's ultimate mistake in this controversy was that he did not realize the need for non-randomized studies of causality in many fields. So Fisher did have some thinking in this, and he did not totally reject non-randomized studies. This can be seen from this quote from this article by Bill Cochran. Cochran wrote, about 20 years ago, when asked in a meeting what can be done in observational studies to clarify the step from association to causation, Sir Ronald Fisher replied, "Make your theories elaborate." The reply puzzled me at first, since by Occam's razor, the advice usually given is to make theories as simple as is consistent with known data. What Sir Ronald meant, as subsequent discussion showed, was that when constructing a causal hypothesis, one should envisage as many different consequences of its truth as possible and plan observational studies to discover whether each of these consequences is found to hold. So, but Fisher did not provide us a concrete methodology to make our theories elaborate. And indeed, formal analysis of observational studies did not start until the 1980s, and we still don't have a good framework to synthesize observational studies today. Okay, I'm gonna skip Fisher's controversy with Neyman, and perhaps also skip the summary of the topics discussed in the talk today in the interest of time. I'm just gonna give some personal reflections after my reading of Fisher when preparing for this talk. I think his scientific ideas are really fascinating, but his personality is also quite complicated. Fisher had an ideal of science, and his ideal of science is free and pure. That might explain why he often had strong views. And Fisher, unfortunately, did not always work out his genius ideas fully. I found this comment by Di Finati quite useful. So he said, Fisher handles with mastery in each individual problems, but rather cavalierly in conceptual matters, thus exposing himself to clear and sometimes heavy criticism. And Di Finati is mostly talking about Fisher's sort of fiducial probability argument. But I think this kind of also applies to some other places, as we have seen in this conference. When reading Fisher's writing, I thought some of his polemic was a bit disturbing to me. I thought, but they're also quite useful to understand how he really thinks and how he views other people's work. So I thought we should all be respectful, but more personality in academic publications can be enlightening and entertaining. And in some sense, I don't see that very often in today's world, and it's a pity. So my next point is, design is a difficult concept to grasp for my generation of statisticians. And Fisher made some very good points about design. And when he initially introduced this concept, he was not just talking about experimentation, but also how data are being collected. And he criticized this kind of setup in the Neyman-Pearson theory that we have repeatedly sampled from a same distribution. So that is indeed the default setup for mathematical statistics today, but that's not quite true for practice. In practice, this is at best an approximation to reality. And Fisher's remark on this was really sobering for me as a young statistician. My last 2 points is I wanted to speculate a little bit about randomization without Fisher. And I think we might really be talking about decades of delay of this idea, because when I look at the arguments from the same period, they were really not as mathematical as Fisher. And even after Fisher made his mathematical justification, it took a long time till randomization to be accepted in many fields. So it's really unclear if we don't have someone with Fisher, like Fisher, then if we would be have such a sophisticated system of randomized experiment today. Maybe it will just be delayed for a little bit. So finally, this is a personal reflection that I think more reading helped me to demystify Fisher, but I also feel that it's just become more and more difficult for me to summarize Fisher in one sentence or one paragraph or even in one article. So I'll end my talk there. Unfortunately, I used perhaps quite a
Thank you very much, Qingyuan. Thank you. Yes.